Hello, everyone. Welcome to PyData Global 2024. We are very excited to have you here. It is my absolute pleasure to introduce Lu Qiu, who is a data engineer at LanceDB, and Allison Wang, who is a software engineer at Databricks, and also an Apache Spark committer. They are here to talk to you about bridging big data and AI. Without further ado, I will pass the floor over to Allison and Lu. Thanks.
Thanks. And hi, everyone. So Allison and I will share the topic about how to bridging big data and AI, basically how to empower PySpark with Lens format for the multimodal AI data pipelines. And I am the database engineer from LanceDB and also the data on Kubernetes ambassador, and previously also the PNC of Allison open source project. And Allison, why don't you just briefly introduce yourself?
Yeah, sure. My name is Allison. I'm currently a software engineer at Databricks and also an Apache Spark committer. Let's get started.
Yeah. Could you help change to the next slide? Thanks. Okay, great. So this is today's agenda. We will basically go through like three main aspects. The first one is we will introduce an AI data lake that built on top of an open source project called Lens. It's a data format. And we will go through like Spark, PySpark, and the Python data source API, basically like give you an introduction for Spark. And lastly, we will share about our latest development about our PySpark Lens connector, so you can try out both functions together. So the AI-driven data lakes with multimodal data can't be a need. So data lake is not a new concept. We have been working with data lakes for past several years, but the AI brings new need for the data lake. Previously, as when we organize information, try to get information from data, we organize them into like tables with small tabular data. And each row is pretty small. It's around like 145 bytes. And each cell probably only a small string or number. But when AI comes in, we have much like larger data for single cell. So we'll try to get more information from the original data. So we create some numerical representation of those original data, which called vectors or embeddings. And a single vector or embeddings is easily around like 4 kilobytes. It's 25 times bigger than the original tabular data. And nowadays, for training, for building foundational models, we leverage the images and video information itself. And images can easily go to like 100 kilobytes, and videos is much larger, it's around 50 megabytes or even bigger. So the data that we are kind of want to use and be able to use have been much larger than before. Yeah, it's basically generate much quicker. And for the training workloads, we also have like multiple like different like data set. Next, please. So we have the Cypher data set is around 160 like megabytes. And after which the training data set like ImageNet is growing to 150 gigabytes. And when we are building some large language model with text only, it's easily around like 10 terabytes. And when we consider images and videos in our foundational models, it can reach the petabytes level. And for the large lens data set, currently is more than 10 terabytes. So basically the training workload training data set have been like several order of magnitude larger every several years. Besides that, the AI data workload also need to enable diverse AI workloads all the ways in the whole pipeline, from analytics workload to training, to exploration, to curation, to evaluation. So all those things need to be able to handle and to be able to access the single like AI data lake and be able to leverage your information. Based on all the needs, so we create this called new CAS theorem and for AI data lake. Basically, like we have like three kinds of major needs. we need to be able to quickly get the information that we want. We want to quickly fast scan the data set and filter on top, search on top to get the data that we want. And for training workloads, especially, we need shuffling. We want to get the data in the order that we want. So a random access is needed. And also when we're doing a bunch of filter or search, in order to do efficient like filter push down, random access can help us to do the search and filter at a much better performance. And after we are able to get our data in the order that we want to quickly be able to stream the data set all the way to the GPU nodes, especially for the original large blocks that's sitting on object store, like images, like videos, want to quickly be able to stream it all the way to the GPU nodes. So these are what we call like the new CAPS theorem. We just created a new theorem. But compared to the old theorem is unsolvable. But this new CAPS theorem is actually solvable. But majority of the existing framework, they target one part of it and solve it really well. And some framework maybe touch two, but they normally don't touch all three of them. We are like, whether it's possible for us to have all those things together, given that we have a joint open source community from Lens and Spark. We have the shared vision to bridge big data and AI to create the new AI data lake. We have the co-author of Pandas. We have the SPNC of Hadoop. We have multiple PNCs from Apache Arrow project. We also have the Spark committer, Ray, Presto, Chino, Pina, Delta Lake, Allison, and a bunch of other open source community, PNC, and committer. Basically, we come down and then think that whether we can have some solutions together. The solution that we create, a foundational piece, is called Lens format. Lens format is the foundation of creating your AI data lake. It's a modern columnar format for AI. Compared to the old like columnar format like Parquet, this format allows you to store much more things. Like we are able to store multi-modal data, like embeddings, images, videos. So basically, even if your table contains some small fields like ID and some large cells like videos and images, you can all put them together in this lens format on cloud storage. And we also support like version manifest to support time travel. We store the schema information to do zero copy schema revolution. And one special thing here is that we also support you to store indexes along with your data. No matter it's vector indexes, Scala index, and full text index. So the search indexes are together with your data set. And because of the cloud storage scalability and the design, we are able to support millions of tables and trillions of rows per table. There's no upper limit of how much tables and rows per table that we can support because of the design. But like I put the numbers here, this is the upper number that we are used in production so far. And remember the old CAPS theorem, the data format not only to be able to store the data and also the other information, but it should be able to support like diverse workloads. And we support the fast random access. It's 1,000 times faster than Parquet. We also support comparable scan performance to Parquet. We support you to do different search directly, no matter it's SQL search or the RAG similarity search, also called vector search, or the full text search for you to search around a bunch of text information. If you are curious more about how we designed this lens format and what design decision that we made, for example, we throw out the row group design, which is important design for traditional Parquet format. And feel free to look at our like GitHub in our GitHub. Basically, we have all the code like open sourced. So feel free to directly read through the code. Or if you are curious about our design, we also have our blog on our blog.lensdb.com website. The PNC from Apache Arrow Project Western have write a bunch of really great blogs, basically share all the details about all the design decisions that we made and what's the reason that we made those design decisions. it's a lot of blocks. So I probably not be able to go through it one by one in here. And one important thing is that this AI data lake is actually also your vector database. So the AI data lake, so as I said before, like we also put indexes together with data. So it's highly scalable. You don't need to store the indexes like other vector database in your memory, which is limited by the memory capability. So in the lens format, we already give you your vector database. And this vector index is this space, is stored in the cloud storage. And we allow you to do compute and storage separation. In many of the vector database these days, they are limited by how much memory you are able to create, able to store the vector index. And even if you have more workload or less workload, the instances to always run there. But in Lens case, the compute and storage is separated because the indexes live in the data set. It could be much larger than the actual one, the active used one. And you can launch the compute instances when you have like more workloads. You have more rack to do similarity search, to do SQL search, etc. And we have a bunch of Scala index and also full text search index to do efficient filter push down. So the Spark connector, the Presto connector, the Chino connector, they can do the filter push down much more efficiently and have much better performance. We can delegate all those SQL filter to the storage engine. And all those things are only make sense when you support random access, because we need to like do vectors index and Scala index to quickly filter out the unneeded information and quickly locate the information that we actually want. And it could be like a bunch of row numbers. And then we need to fast use random access to get those row number, those row information from the large like data lake. So this only makes sense when you support random access. Otherwise, the performance will be really bad. And to quickly try out the vector database functionality, we created an open source embedded vector database called LensDB. So LensDB basically is a library that you can use it to leverage the functionality of the Lens format. It's pandas and PyArrow compatible. Basically, you can create your data in the pandas or PyArrow format, and you can create the lens table with those existing pandas or PyArrow data. And after which, you can create the indexes. We can create your vector index or create your full text search index or the other index. And then you can do a bunch of search and filter on top of the data set. So for here, you can search with your query about like, oh, which data is most similar to my request. And or you can directly give it embeddings, basically represent the same thing. And this open source embedded vector database can embed it in the application itself. It basically is serverless. You just need to do import LensDB and create a table, create the index, and do your search. So it can be pretty lightweight because all the information like the data and indexes information is stored on the cloud storage directly. But here we just handle the search workloads. And also we also have a GitHub link that if you guys are interested, feel free to directly take a look at the source code. And also we have a website, I've already forgot to link here, that you can go there and then understand what API and what functionality that we provided through this example embedded vector database. And if you want to serve a large amount of workloads, you want to serve a large amount of like vector search or similarity search in your rack stack, then we also offer the distributed vector database in our cloud offering. So this one, we basically maintain a bunch of like query nodes for you, just like maintain a bunch of like open source embedded vector database for you. And those are independent compute scaling. Because of the distributed nation, we are able to support tens of thousands of queries per second and hundreds of rows per second write throughput. And the same as before, like millions of tables and trillions of rows per table. We have the, if you look at the left side, we have the query fleet that basically serving the user request. And it will have a load balancer like route to different like query fleet. And on the back end, we have the caching, we have the indexer to improve the read and write performance. And in the backend, all the data are stored in the lens format on the cloud object storage. And lens format or LensDB are not just for Whitehair database. We are a unified AI data lake that for the multimodal AI data pipeline. You can use Spark to quickly generate a large amount of data and write to your lens format. You can use DuckDB or Trino or Presto or Spark to do the analytics from this database to generate your report, to understand the data, to do exploration, or to basically do some data understanding. And you can use Ray and PyTorch on this data set for your training workload to quickly streaming all the information that you want to your training workload in the order that you preferred. Because it can also support images and videos, all kinds of like AI data set. And you can also use LensDB for the serving and search workloads, like the similarity search for the RAG and also the SQL search directly. And now I will hand it to Allison for the more information about how we can work with PySpark.
Great, yeah, thank you, Lou, for the super awesome introduction. Yeah, I really enjoyed this introduction. Yeah, so as Lou mentioned, LensDB is a super powerful and performant vector database. But the very first step to use LensDB is to convert your data into the lens format. So this process is often challenging because data is often messy and they're saved in many different formats such as CSV, JSON, Parquet, and they're pretty much scattered across various locations such as the cloud storage and different databases. So oftentimes there's a gap between cleaning and transforming various datasets and leveraging these datasets for machine learning and AI use cases. So in this part of the talk, I will explain how we can use a new feature in PySpark to bridge the gap between the big data and AI by directly writing the transformed data into the lens format. So here's a quick intro to Spark. So Spark is an open source unified data processing engine. It is often used for the ETL process in the data engineering. And it is production grade, widely adopted by many companies. So Spark is designed for the big data workloads, but it can also run on the single node setup. So making it suitable for everything from the local development to the enterprise grade production environments where it can scale up to thousands of nodes to handle petabytes of data. So Spark is open source and the open source community is very active. So there are more than 3,700 contributors from both the industry and academia. So PySpark is the Python API for Apache Spark. It basically allows you to interact with the Spark engine using Python. And it is incredibly popular. So we have more than 30 million monthly downloads on PyPy. So here's a quick example of PySpark, where you can convert a pandas data frame into a Spark data frame and try out all the Spark features. So one of the key features in Spark that I want to cover today is the Python data source API. So it is a new feature in the upcoming release of Spark 4, and it is a game changer for building custom data sources. So before this API, Spark only has the Scala data source API, which can have a pretty steep learning curve if you're not familiar with Scala. Now, with this new API, it becomes much easier to develop data sources for Spark. So this API supports many functionalities, including distributed reads, atomic writes, and also support both batch processing and Spark structure streaming. So one key feature is that this API leverages Apache Arrow for efficient data transfer between Spark's JVM process and the Python process, so making it ideal for developing connectors that also uses Apache Arrow under the hood, such as Lens. So now I will explain how we can use this API to build a PySpark connector for Lens. So here's an overview of how Lens Spark connector works. So Spark is a distributed engine, and it has two main components, the driver and the executors. So when writing a Spark data frame, each executor handles one partition of the data frame. And each executor will create a Python process, and then pass an iterator of arrow record batch to the Python process. So these record batch represents the rows in the partitions. And then the Python worker can directly use Lens API to write these arrow record batches into Lens fragments or Lens files. So once this process is complete, the Lens API will return a list of fragments back to the Python worker, which is then sent back to the Spark executors and then to the driver. So after all the tasks are finished, Spark driver will commit the write process, and it will use the fragment metadata that received from the executors to publish the new Lens dataset by updating the manifest files. And you can also add any custom logics to clean up the files if any of the write task fails. So here is an example implementation of the Lens writer using the Python data source API. So this is just part of the implementation. And if you want to see the source code, feel free to scan the QR code here. So as you can see that using the Python data source API and leveraging Apache Arrow, it is very straightforward to implement a writer. So the write method here is just 3 lines of code. It takes an iterator of arrow record batches and write them into as a lens fragments. And this entire write process will run on the executor side for each partition. And the commit method here is invoked on the driver side after the write process completes. And it takes a list of commit messages that are just collected from the executors and use the Lens API to finalize the write operation. And here is how you can use the Lens Spark connector. It's actually very easy. So first, you need to register this custom data source into the current Spark session, which will make it discoverable by the Spark read and write API. And next, you can basically convert a Spark data frame directly into the Lens format using the data source, using the data frame write API in a distributed fashion without any intermediate steps. As you see, as you can see from the screenshot over here. And next, you can load this Lens data back as a Lens dataset and take full advantage of all the features that Lou mentioned earlier. Okay, yeah, that's all for the presentation. And Lou, you want to jump in for the last part?
Yeah, thanks everyone. So if you guys have more questions about Lens like Spark integration, and also LensDB library database, feel free to join our Discord, like by basically the QR code here. I also put some link here about like our website link, our GitHub repo, and also our beta cloud offering. And thanks everyone. Any questions? I saw there is a question that asking about like does LensDB support Unity catalog before? And so I already mentioned in the Q&A like chat about like we put the catalog, basically the table format inside our LensDB like repo. So the table format, you can do the versioning and leverage different namespace, etc. So those are basically included in our LensDB, but it's a pretty like thin layer. So if you want to leverage like more functionality from the Unity catalog, there probably need to have an integration. I'm not 100% sure like whether we already start the integration or not, but this has been a long asking feature like since the last really great Spark Data and AI Summit. Many of people like come to us and ask for this integration. Yeah, I think we may consider like working on it like pretty soon. Oh, that's great. They have a question page that you can take a look. Yeah. Any other questions? I think if no other questions, we can end the session here. And thanks everyone for attending.
Yeah, thank you everyone.
Thank you again, Lou and Allison, for the talk. And just a reminder to everyone, there is a Discord channel for PyData Global. If you guys want to continue the discussion there, you're very welcome. Otherwise, we will see you at the next session.